heet u van harte welkom op de openbare doctoraatsverdediging van de heer Francisco Mesquita. Een verklaarde zitting voor geopend. De heer Francisco Manuel Gonçalves Mesquita, Master in Mechanical Engineering, heeft aan de faculteit een proefschrift voorgelegd handelend over Unidirectional interply fibre-hybrid composites, longitudinal tensile failure and interactions between fiber types. Unidirectionele interlaag, wezelhybride composieten, longitudinale trekfaling en interacties tussen wezeltypes. En dit tot het verkrijgen van de graad van doctor in ingenieurskunde. Hij zal dit proefschrift nu verdedigen. Ik vraag aan de kandidaat om eerst een uiteenzetting van ongeveer 45 minuten te geven over zijn werk. Daarna zal er gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Meneer Francisco Manuel Gonçalves Mesquita, u hebt het woord.
Thank you. Okay, so welcome to my public defense, today in a very different setting, but hello people from YouTube. So I will start by explaining my thesis, but before I dive into the thesis itself, I just want to break down the words in the title. So things like what are composites, unidirectional composites, interply, fiber hybrids, longitudinal tensile failure, and also interactions between fiber types. So let's start with composites. Where have you seen composites? Between other things, you've probably seen some of these wind turbines. And wind turbines actually only work if they're made of composites. If they're not, they're actually not economically viable. Another application that you may have seen on the road is the BMW i3. It's an electric car, and yes, this is the chassis of the BMW i3, and two people can lift it. This is only possible because we have it made of carbon fiber composite. Then there are applications for sports, for example, bicycles made of carbon fibers, and also applications for defense, like the Kevlar vests, which are made of aramid fibers, for example. But what are hybrid composites? Well, if we add fibers, and there are other kinds of composite materials, like concrete, for example, is a composite, or metals and ceramic composites, but here I'm going to speak about fibers and the plastic. So if you have the fibers, and we add a plastic matrix to it, and we put everything together, there you go, you have a composite material. Now, which kind of fibers? One of the most common types of fibers used in composites is carbon fibers, and this is the most classical image that you'll ever see of carbon fibers. The big thing is a human hair, and the small fiber is a carbon fiber, which is 7 micrometers in diameter. But there are also other kinds of fibers, for example, glass fibers, or natural fibers such as flax or bamboo, which come directly from plants. So if you want a more biosustainable composite, you can use flax fibers. And then which kind of plastics? For example, one of the most structural resins that exists are epoxies. Maybe you have seen this kind of tables in social media or YouTube where they make these very beautiful rivers. But the most common things that you may have seen out there are polypropylene bottles or polyethylene bags. So basically, if we melt the fibers with these plastics, we can get a composite material. Now, why do we use composites? That's what I'm trying to convince you here. So if we take 7 grams worth of composite, which is 10 centimeters long, and we hold it on one side and attach 5.5 tons to it, it actually will deform only 1 millimeter. Of course, you can also do this with other kinds of materials, such as steel. You can do exactly the same thing, but in this case, you actually need 20 grams, which is 3 times heavier than carbon fiber composites. So you may say, okay, then let's use plastics. Plastics are very light. Yes, but they are not very stiff. So if you want to use plastics to do this, you actually need 2.8 kilograms, which is 400 times heavier. So composites have the advantage of being very light and very stiff and strong. By the way, if you're wondering, 5.5 tons is this guy. So which kind of architectures can we have in composite materials? Unidirectional composites, as it's in my title, are composites where all the fibers are aligned in one direction. But these are not the only kind of composites we can have, because we can have fibers oriented in multiple directions, and we get a multi-directional composite. For example, the one I'm assembling here is a quasi-isotropic composite, and it has almost the same properties in all the directions. But we don't have to add layers to make multi-directional composites. We can have one layer with fibers in both directions, and these are the textiles, where we can have woven composites, or also braided or knitted composites. So these are kind of fibers that are arranged like our clothes, so in a textile, and then we add the matrix to it, and we get a textile composite. Now, I'm focusing here on unidirectional composites, because when in any kind of composite, the fibers that trigger the final failure in tension are the fibers oriented with the loading direction. So if we look at how a unidirectional composite fails, here we are loading a carbon fiber composite in tension, and as you see in a moment, it will fail very explosively, very brittly, and without much warning. But what's actually happening inside the composite as we are loading is that fiber breaks are accumulating inside the composite, and this will trigger the final failure of the composite. So fiber breaks will start accumulating more rapidly and more rapidly, and at some point the composite will fail, and this will also determine the stress strain diagram, which is the way we characterize materials. So if we have the stiffness, which is the slope of this line, then we can also know the strength and the failure strain, and this can characterize very well our material. Now let me just give you another application where this sudden failure happens, and this is maybe something you've seen before, where you've seen this wind turbine blade failing explosively without any warning. And this, as you may imagine, this is quite dangerous for the applications. So in order to avoid this, we should be able to predict better when this is going to happen. And on top of that, I would suggest to add some more safety to it. So for this, we can use hybrid composites. With hybrid composites, you actually get this pattern over there, which is the carbon fibers ply failing. And this pattern can serve as a warning to the final failure of the composite. So before we get something explosively like we see here, we can actually get this nice pattern. But what are these hybrid composites? As I said before, if we add fibers to a matrix, then we get a composite material. But if we have at least two fiber types, and normally we call them a low elongation and a high elongation fiber, because one is more brittle, the one is more ductile, and we add a matrix to it, there you go, we have a fiber hybrid composite. And the way this works is that if we look at the stress strain diagram of the hybrid composites, if we have the low elongation composite, it's stiffer but also more brittle, and the high elongation composite is more compliant but also more ductile. What we get in a hybrid composite is something in the middle. So we get the failure of the low elongation fibers here, but then the composite still is able to carry load up to the failure of the high elongation fibers. Which kinds of hybrid composites then? So the one I showed you before, and it's also shown in this image, is an intra-yarn composite, hybrid composite, where all the fibers are mixed very well, very closely in the same bundle. But we also can mix them in bundles in the same layer. So the fibers are dispersed in bundles. Or lastly, we can have interply hybrid composites, in which each ply corresponds to one fiber type. Now I've decided to focus here in my thesis on this type of hybrid composites because it's easier to manufacture. You just put different layers of different materials on top of each other. There you go, you get an interply hybrid composite. Therefore, since this is so easy to manufacture, it's quite relevant for industrial applications. Another reason is because if we look at this diagram, we can actually obtain different failure mechanisms just by combining different fractions and thicknesses of materials. So looking a bit further, what we see here is that we have the relative fraction of carbon fibers on the horizontal axis and the thickness of the carbon layer on the vertical axis. And with this image, we can see that by changing the configuration of our hybrid composite, we can obtain ply fragmentation, which is the failure mode you've seen before in the video. Or you can also, if you have too much carbon fibers, you can get immediate fracture, because everything fails at the same time and the glass fibers cannot sustain the loads. But if the carbon ply is quite thick, then also the plies will detach from each other. And if you look closely into this diagram, you'll realize that as we go horizontal to the right on the horizontal axis, we are adding more carbon fibers, less glass, and therefore we're making the composite stiffer. And if you go down on the vertical axis, we are decreasing the thickness of the layers, so we are making the composite lighter. So actually we want to push against this line because we want to optimize the performance of our hybrid composite. But we don't want to go over it, otherwise we enter the region of immediate fracture, and that's not good. So what we want to do is to be able to predict the longitudinal tensile failure of fiber hybrid composites, so that we can go very close to that line but not go over it. And by doing this, we can gain confidence on the materials, but I don't only want to do that, but but I also want to be able to connect the micro-level fiber properties and matrix to the meso-level failure modes of ply fragmentation, immediate fracture, and delamination. So let's establish a roadmap. So the goal is to develop a model. But as I told you before, when we are loading the composite in tension, what we are starting to get here are fiber breaks. So in order to be able to predict these fiber breaks, the first thing we need to know is how to get the fiber properties. So let's start by characterizing the fiber properties. One thing I didn't tell you is that apart from the fiber breaks happening just because of the fiber strength itself, they also happen because the fiber breaks, when they are when they occur, they create stress concentrations around them. So other fibers carry extra loads, and we need to understand how that happens. So extra loads, like I show here, so the broken fiber in the middle, and then the surrounding fibers have stress concentrations. So second step of this is to understand how these stress concentrations occur. And finally, our model is not really useful if we have not validated it against experimental results. So the final step in this research is to validate the model. And I want to do this not only against the stress-strain behavior, which is a global behavior, but I also want to look inside the composite and compare the damage mechanisms that are occurring inside. So starting by the characterization of fiber properties, what we would wish is that the fiber strength is a value, is let's say 10, 100, 1000, 10,000 megapascal. But in reality, it's not like this. In reality, fiber strength is stochastic. And this means that the fiber strength is random, but obeys this variable, this distribution, this probability distribution. Now, this distribution is characterized by this equation, and I know you guys don't like very much equations, but very simply, this is the strength, so this is our independent variable in this x-axis, and the sigma 0 is the scale parameter. Basically, it's that value. It represents 68% probability of the probability density distribution. So basically, if you change this, you move the probability distribution left or right. And then you have the modulus, which controls the variability. So higher modulus means that we have less variability on the fiber strength. And of course, just to let you know also that fiber strength is stochastic because it's determined by the defects inside the fiber. Due to the manufacturing, there are very small defects, nano or micro level, and these determine the failure of the fiber. So that's why we have a probability distribution. So if we make fiber longer, it's more likely that we have a defect inside of it that will trigger its failure. So this is also depending on the fiber length. Now, if you do some mathematical arrangement of this, we can actually convert this probability distribution into a line if we apply some logarithms here. And the way we want to characterize this is by putting some data points over there. And I removed the length parameters there because normally we do this for one specific length. And if you wonder that this equation is a bit complicated, actually this is just a line equation where we have the y equals mx plus b. So this is, once we have these data points, that's quite simple. The problem is getting these data points. So let's do that. What I did here was to partner up with Diastron, who have automated single fiber testing machines. And what they have is basically this equipment. This is the core of the equipment, where they have a laser diffraction system to measure the fiber diameter at multiple points. And then if you get the average of this, you get a very reliable measurement of the fiber diameter. And also they have the tensile tester, which enables us to get the force and displacement diagram. And with some data processing, we get the strength of the fiber and also the stiffness of the fiber. Now, stiffness is not a unique parameter in carbon fibers because they actually stiffen with the applied strain. If you measure the stiffness between 0.1 and 0% and 0.3% strain, we get a certain value of stiffness. But if we move that range a bit further and further, we can actually measure the stiffness as a function of the applied strain. And when we do this, we get a diagram like that, and we can fit a line to it, where we get the gradient of stiffness, so how much does the stiffness increase with the applied strain, and what was the initial stiffness before the applied strain, or at least an approximation of this value. And I did this since I'm talking about hybrid composites. I'm not going to do this just for one fiber type. I actually did it for 5 different fiber types. 4 of them are carbon fibers, 1 of them is glass. And the reasons I did this is because two of the fibers, for example, the T700 and 34700, they have the same stiffness and tensile strength according to the manufacturer. So I wanted, first of all, to compare these two fiber types, see how their available probability distributions look like, and understand how this may influence the composite properties. Then I also tested the T300, which had, again, similar stiffness to the previous two, but a lower strength. Let's see how that influences the label parameters. And the HS40 fiber, which has almost twice the stiffness, but the same tensile strength. And since most of my hybrid composites will be with carbon and glass, then also I tested this glass fiber, which has a lower stiffness than the carbon fibers, but a very not so different strength because it's also more ductile. And then I did a very high number of tests. If you add all of these tests up, it will get you to almost 700 single fiber tests. So this is 700 times putting fibers in a cassette, plus extras, which I'm not even taking into account here, which are to make some calibration. So, first of all, let's look at the fiber stiffness and fiber stiffening of the carbon fibers. And what you can see already here is that these three carbon fibers, T700, 34700, and T300, they have the same initial stiffness, or very similar initial stiffness, but they don't stiffen at the same rate, all of them. For example, this one stiffens at 11 gigapascal per percent of applied strain, but this one is 31. So this tells us that carbon fibers are not all the same. Even though they have the same initial stiffness, they don't stiffen the same way. And it's important to understand that we have to characterize each fiber very well before putting it in the models. And then when we look at the HS40 fiber, yes, it stiffens a bit at a faster rate than all the others, but the most unexpected result here is that this initial stiffness was too high compared to the datasheet value from the manufacturer, and we were not expecting this. So what I did next was to put these fibers in a composite and test all the composites, all the unidirectional composites, and what I obtained was this. So this dashed line is the stiffness given by the manufacturer, and here are my results, quite well wrapped around the datasheet value. But composites, the fibers in the composites, they are not always perfectly aligned with the loading direction. They have some misalignment, some waviness, some angle with the loading direction. So it's possible that the value that we measure with a single fiber test, which is this value by the way, is a bit higher than the value obtained through the composite tests, is actually real, because with some misalignment, this stiffness measured from the composite is a bit lower. So this seems that when the manufacturer measured the stiffness, he measured it like we did with composite tests, and then you obtain a certain stiffness, but the real stiffness of the fiber is a bit higher. And when we look at the glass fibers, actually we find something remarkable here. What happens is that although the carbon fibers stiffen with the applied strain, the opposite happens with the glass fibers. So actually the stiffness decreases with the applied strain. And this is remarkable. This has not been observed yet in the literature. And we think, although we are not 100% sure, that it's because the silicon and oxygen atoms in the glass fiber, they get a bit further away as we stretch the fiber, and this reduces the energy of the bonds, and therefore our stiffness decreases. Again, to be confirmed, we are not sure about this, but it's our hypothesis. And then looking at the strength, the most important thing I wanted to look at was the comparison between the T700 and the 34700 fibers, so the blue and the red lines here. And as you see, indeed the sigma 0, so the scale parameter, is quite similar between the two fibers, but the modulus is not the same. And this means that the variability of strength of the fibers is not the same between the 34700 and the 3300, and this may have consequences for the composite properties. Now, when I said that we needed a lot of tests to characterize properly the available parameters, I didn't tell you how many. And in fact, it's very difficult to say how many tests we need exactly, but what I did here was take a sample, for example, of 50 points out of my 217 data points for the T700 carbon fiber, and for each set of 50 fibers, I fitted variable parameters. And if we do this enough number of times, we can actually fit an ellipse to encase all these estimations. And of course, if we have a low number of fibers, we can get a very big scatter in the parameters, but as we increase the number of fibers in our sample, this ellipse shrinks and shrinks until we get a focal point, which is the value I obtained with the 200 tests. So this is to say that we should not use only 50 tests to characterize the fiber strength, at least for the T700, because we get a very big scatter here on the parameters. I cannot say how many we need, but definitely a very high number. But then there are also other ways of characterizing the label parameters of our fibers. And I tried a new method, another method, using composites. Not single fibers, but a composite. I took this specimen here, which is quite a small specimen, let's say like this. And I put it in a computed tomography machine, which basically shoots X-rays through the sample, which is rotating at the same time. And with this, we can get a volumetric image of our composite. Now, using this, we scanned the notch region where the composite actually is going to fail and will accumulate more fiber bricks. And we were looking for the fiber bricks. So, doing this, we can actually correlate the stress applied in the composite with the accumulation of fiber bricks, and we can separate the fiber bricks that happen due only to the strength of the fiber and the ones that occur due to the stress concentrations. So, when we do this, we can actually estimate the variable parameters using a virtual bundle with assumed variable parameters. And by doing this, before we compare with a single fiber test, because this will be our benchmark, I actually need to scale the variable parameters estimated through the composite that we imaged only 1.7 millimeters up to the length of the fibers in the single fiber test, which was 12 millimeters. So when we do this and compare for the 34700 carbon fiber, we see that the estimation using the singleton CT is actually gives us quite decent estimations. For one specimen, it was quite spot on. For the other one, slightly lower, but still within the scatter. But when we look at the estimation for the glass fibers, this didn't go so well. And I think the problem is not the method itself. It was the specimens that we had with this fiber type. Since glass fibers are a bit bigger, we had fewer of these fibers in our composite, and therefore we didn't have enough statistical power to predict properly the variable parameters. So next time, and I hope we can do this later in the year, we'll take a bit bigger samples and be able to check whether this is a problem or not. Okay, so bit of chat. We finally managed to characterize the fiber properties. So let's go to the second part and try to understand stress concentrations. So what are stress concentrations, and are they important? So let me show you this image here where we have 4 states in our composite. An initial state where all the fibers are intact, and if we apply a load to it, then all the fibers are carrying the same load. But at some point, due to the stochastic nature of fiber strength, one of the fibers will break. And when this happens, due to the matrix, the fiber will still recover its stress a bit farther away, but also the fibers nearby will have to take over these stresses that the broken fiber was carrying before. So these fibers that are nearby are more likely to fail. So if we increase a bit the strain, or even just like that, the fibers nearby can actually fail just because of these stress concentrations. And this will accelerate the process of composite failure and lead to the final failure. Now in hybrid composites, as I've shown you before, we have different failure mechanisms such as ply fractures or catastrophic delamination. So we're not only interested in the stress concentrations due to the fiber breaks, but also due to the ply fractures. So I'm going to investigate not only stress concentrations due to fiber breaks, but also on the higher level with ply fractures and also some delamination. So starting with the fiber breaks, I continue to develop this model that we see here in the screen, where basically we have an applied displacement on one side, while on the other surface we hold it, except for the fiber in the middle, which will be our broken fiber. And with this we can get the stress profile in the broken fiber, and which we can characterize with the ineffective length, which is the length over which the fiber recovers 90% of the nominal stress. And on the intact fibers, we get a stress profile like this, where you have a maximum stress concentration, and then the stress concentration decreases and returns to the nominal value. So, since I'm studying hybrids, I decided to do a little bit of study on interply hybrids using this model. And what I did here was to make this broken fiber with the X a bit further and further away from the ply interface. you see here, this fiber is further away from this interface than that one. And I tried to see, is there an influence of this distance on the ineffective length? And what I discovered is that there is not really a big influence. For example, this R squared is quite low, so there's not a big correlation between the ineffective length and the distance to the ply interface. But I tried something else. I looked at the local arrangement of the fibers and tried to look at the local volume fraction. And this local volume fraction is basically the distance between the broken fiber, the reference fiber, and the fibers nearby, and can be characterized by this Voronoi polygon. So this Voronoi polygon is bigger if the fibers are further away, and is smaller if the fibers are nearby. And the local volume fraction is basically the area of the fiber divided by the area of the polygon. So if there's a lot of compacted fibers, the local volume fraction will be higher. And here, indeed, I found a very big correlation between the ineffective length and the local volume fraction, which means that this local volume fraction affects much more the ineffective length, the stress recovery of the broken fibers, than the distance to the ply interface. Looking at the higher level ply fractures, I created a new model, and it works more or less the same as the previous one, where we apply displacement on one side, but in this case we hold only the intake layer, and we release the broken layer. So this broken layer will be simulated here. And I did this for 3 different composites with varying thicknesses of the broken layer. And when I did this and looked at the ineffective length, I found that the ineffective length depends very much on the thickness of the broken layer, and also that the ineffective length is much higher in the ply fractures compared to the single fiber breaks, which is this smaller value over there. Which means that the stress recovery in the ply fractures occurs at a much larger scale compared to the single fiber breaks. Looking at the maximum stress concentrations, again, stress concentrations due to ply fractures are much higher compared to single fiber breaks, and they also depend on the thickness of the broken layer. And finally, I also looked at the lamination. The lamination, by the way, is when you have a ply fracture, so the broken, the ply fails in the middle, and then the layers debond from each other. I created this model which has exactly that property. So again, we hold the intake layer, we apply displacement on the other side, but now this face, the red face over there, can slide. So the layers can slide on each other. And I ran some simulations with 3 different delamination lengths, and I wanted to see what is the effect of the delamination length on these stress concentrations. And looking at that fiber, which is close to the ply interface, what we observe here is that the maximum stress concentration actually decreases as the delamination length increases. And this is not really because the fiber is less affected, but it's because the stress concentrations become more uniform through the thickness. So if we look at the fiber that is a bit farther away, the opposite happens. So the fiber has a higher maximum stress concentration that is increasing with the delamination length. Okay, so 2 steps are done. We characterized the fiber properties and understood something about stress concentrations. So let's start developing our model. So the way this model works is that we have all the fibers parallel to each other and with the loading direction. And in order to take into account the stochastic fiber strength, we divide each fiber into small elements like that. So each of the elements will have a random strength according to the available distributions. When we start applying load into it, we see that at some point we will have fiber breaks, because the weakest fiber of all will start failing. And to this fiber we'll apply this stress recovery profile as we obtained from the finite element models. Now, the fibers that are nearby will have the stress concentrations, and the way we take this into account is that we get the data from the finite element models, we pass it through this surface approximation, which has the dimensions in the radial direction, so distance from fiber to fiber, but also in the axial direction, so distance along the fiber. And using the data from the finite element model, we can get this surface approximation, where we get the average stress concentration, so we don't take into account this big scatter, we just follow average value, simply because we don't know, well, we know what characterizes, but we cannot really predict well this scatter yet. So allow me to rotate this model for you and to remove these glass layers, because I want to show you how we model ply fracture. So fiber breaks will start accumulating, but at some point this fracture, this ply will fail. So let's consider that we are at that stage and we have one fiber break over there. But due to the stress concentrations only and without increasing the strain, these two fibers that have the stress concentrations can fail. So in the second iteration, we get 3 fiber breaks. Now the stress concentrations are even higher. So in the third iteration, we can get more and more fiber breaks. And at this point, we can say, okay, the number of fiber breaks is increasing rapidly enough for us to say this ply will fracture there. But we don't want to continue the model to calculate which of the fibers will fail next based on the stress concentrations. We want to actually predict this because that is much more computationally cheap. So we look into the elements of the fibers that are not broken yet, and we calculate this failure index, which is basically the strength over the strength, the stress applied over the strength, and gives us the probability of each fiber element to break. And the one we break is the one with the maximum failure index. So we can calculate the morphology of this ply fracture without letting the model continue and consume the computational resources. So if we look at the influence of the available parameters of the S-class fibers on the composite properties, I did this for 2 stacking sequences, and I maintained the parameters of the carbon fibers and changed the available scale parameter of the glass fibers. And when I did this, I was able to change the failure mechanism. Which failure mechanism? Let me remind you. So if we have applying tension and we have applied fracture and everything fails immediately, we get immediate fracture. If when the glass ply fails, we already have some fractures, we can call it multiple fracture. But if we are at the point that the carbon ply has so many fractures that cannot fracture again, then we call this saturation. And for the other kind of composite with multiple carbon plies, we can have an intermediate step where you have some of the plies that are saturated, some of the plies that only have a few fractures, and we call this partial saturation. So the result of all this study ends up in this diagram. And this is a probability diagram because each of these bars corresponds to 100 simulations. So when we run the simulations with each set of parameters, we count how many times did immediate fracture happen, saturation, multiple fractures, and we can get this probability map. And what you see here is that when the glass fibers are too weak, then we always get immediate fracture on the left side. But as they get stronger and stronger, we start coming into modes of multiple fractures and finally saturation. And all of this means that even with the same set of parameters, due to the random nature of the fibers and their strength, we can get multiple failure modes. So this diagram, coming back to this diagram, this hard line that is here between ply fragmentation and immediate fracture is actually not a hard line, but rather a probability distribution, a probability transition. Next, let's talk about the lamination and how we model the lamination. So looking a bit closer here, what we have is that the stress at the ply fracture surface is 0, but the stress in the glass fibers is higher. There is stress on these fibers. So we get here a shear stress. We get some stresses in the interface, and this can cause delamination. So how do we deal with this? If we consider that we have a certain delaminated surface of length A, and we want to check whether this delamination will increase of a increment delta A, what we have to check is basically this equation. This equation seems a bit complicated, but actually just means that if the energy that is dissipated by the increase of delamination is higher than the energy necessary to create the surface, then this will occur because the composite will try to go to the lowest energy state possible. So how do fiber breaks influence any of this? Well, in the equation that I showed you before, without any influence of the fiber breaks, nothing says that everything says that the lamination length on the left side and on the right side of the ply fracture needs to be the same. But actually, in our experimental observations, we don't see this. We see that one of them is typically larger than the other. And one explanation for this is the presence of fiber breaks. Because if we go back to this equation, this US is the strain energy. So it's the energy contained in the fibers. It's the energy that the fibers release when they break or when the delamination length increases. And therefore, if we have already fiber breaks, they already released some of that energy, and there's less energy to release. So the lamination will not increase so much on the side that have more fiber breaks compared to the side that have less fiber breaks. So just a simple study, presence of fiber breaks versus no presence of fiber breaks, and what we see immediately is that when we have fiber breaks, the initial delamination length, so that occurs immediately when the ply fracture happens, is smaller than the case without fiber breaks. And this is, again, because we have less energy to dissipate, so the delamination length will not increase so much. Now, if we invert a bit that equation over there, we can also get the energy release rate, this G2. And this G2 is affected by the energy release, which is controlled by the fiber breaks and by the energy of the material, but also by the friction. And this is why this energy release rate decreases with the increase of the delamination length, because there's more frictional buildup, and therefore there's less energy that can be, there's more energy in this friction. But what I want to actually compare here is again the case of no fiber breaks against the case of the influence of fiber breaks. And on the case of no fiber breaks, again, the energy release rate decreases, but there is no difference between the left and right side. So this delamination will always be symmetric if we don't have the fiber breaks. But in the case that we do have them, then things are a bit more complicated. So in this case, the energy release rate on both sides is different, and this ends up in a natural asymmetry of the delamination length due to the presence only of the fiber breaks. Now, another thing I did here is that, I think this is the last time I'm going to show you this graph, I'm sorry. This line, horizontal line over there, basically defines whether the composite will delaminate or suffer some delamination or not. And this depends a lot on the energy of the interface, the energy we need to break the interface. So if we change this critical energy release rate, we can also change this line and make it more or less likely for the composite to delaminate or not. So when I did this, I varied from 0.1 to 1 Newton per millimeter, and indeed I obtained different failure mechanisms. For example, the gray line is a failure mechanism of ply fragmentation. The orange one is the case of catastrophic delamination, and the intermediate case, the green curve, is the ply fragmentation plus delamination. And the most interesting result here is actually that we maximize the failure strain, not with the lowest or highest critical energy release rate, but with an intermediate value. So we can find a way here to optimize the failure strain using this strength of the interface. Okay, so I showed you what we can do with our model. So let's check whether it works actually to predict the strength of composites. So we go back to the synchrotron, where we do the volumetric images of our composites. And we tested a cross-ply composite with fibers aligned with the loading direction and surrounded by fibers which are in the 90-degree orientation. And we do this just to keep the composite from splitting or avoiding some of the splitting. And I tested not only carbon fiber composite, but also two of hybrid composites with different configurations. And those are the glass fibers, the white ones, and the more gray ones are the carbon fibers. And if we compare the stress strain diagram, experimental stress strain diagram with the modeling that we did, we see that, okay, we are capturing the stiffness quite well, not very difficult, but we are failing quite a lot on the failure strain and strength of our composites. But this diagram doesn't tell us much more than that. Okay, we are failing, but what is going wrong? What's not being done properly? So let's look a bit deeper. Let's look inside the composite and see how the number of carbon fiber breaks increases compared between the experiments and the model. And we see that initially we are not capturing so badly the increase of the number of fiber breaks, but then the model just continues to run until it fails at a much higher stress level compared to our experiments. Okay, we're going to this level, but let's go a bit deeper and understand exactly what is going well and wrong here. And if we look at one plate density, and one plates are fiber breaks that are isolated from all the others, so they are breaking only due to their strength, stochastic strength, and not due to any stress concentrations. And if we would look at the two-plate would be two fiber breaks very close to each other, and these ones break due to stress concentrations as well. So if we are capturing well the one plate density, it means that the natural strength of the fibers, the stochastic strength of the fiber, we are capturing it well. So yes, we are capturing well the available parameters. But if we look at the duplets, here things are not so great. And this means that we are not capturing well the stress concentrations, but not the static stress concentrations that I've shown you before. I think what we are missing here are dynamic stress concentrations and also local stress concentration. So these are other kinds of stress concentrations that occur when the fiber breaks, or very local, meaning in a certain region of the fibers. So this is what we need to improve to be able to get better predictions of the composite strength. Now, the last thing I want to talk to you guys about is about the hybrid effect. I showed you this image before, where we have the stress strain curve of our hybrid composite, and it's not really a coincidence that the load drop, the first load drop in the hybrid composite, occurs at the higher strain compared to the low elongation composite. It's actually called the hybrid effect. And this hybrid effect occurs between, due to these three reasons. These are the three main hypotheses that support the hybrid effect. The thermal residual strains, because fibers have different heat expansion properties. So when we add two different fiber types, one will contract more, the other one will expand more, and therefore we'll get some residual strains, dynamic stresses, so stresses that are released at the moment of the fiber break. In hybrid composite, they actually cancel each other a bit, and the interactions between fibers, which is what we actually capture in our model. Now, there was a study before my PhD on the influence of the thickness of the different layers on the hybrid effect, and it was shown that the thinner the layers were, the higher the hybrid effect was. And this is exactly what we observe also in our experiments. So the thinner the composite is, so the hybrid one was the one with the thinnest carbon layer, the carbon fiber break density is actually able to be much higher, so the composite is able to accumulate much more damage compared to the reference carbon fiber composite and the one with more layers that can interact between each other. So this is experimental evidence and supporting role of the fiber breaks in the failure development that we had not seen before. Now, there was something interesting that I observed when I was analyzing the data, and that was that the fiber breaks seemed to occur closer to the ply interface almost all the time. But I was not sure whether this was just me looking more into these fibers or if this was really something that was happening. So I went ahead and calculated the distance between each fiber break and the ply interface. And when I did this, I noticed that indeed, it's more likely that fibers breaks will occur close to the ply interface than farther away from it. And this gives us some supporting information to the hybrid effect, because if we have a low elongation fiber composite with one fiber break in the middle, surrounded by only fibers of the same type, and we want to check whether the other fibers will break or not, well, it's likely that any of these 6 fibers will break because they are more or less the same failure strain, so one of them is likely to fail. But in a hybrid composite, and especially if the fiber breaks occur more likely on near the ply interface, in this case, it's less likely that a new fiber break will occur because there are fewer fiber breaks. So this is again some amplification effect due to the fact that we have weaker fibers near the ply interface compared to the middle of the plies. So finally, just to conclude, we were able here to connect the micro to the meso level. So we were able to connect the properties of the fibers, the scale, and the interfaces to the failure mechanisms of hybrid composites. I also developed a new method to estimate the available parameters, not doing 200 single fiber tests, but just by doing one composite test. Created new models to predict SCFs, and also got some more understanding on the underlying mechanism of the hybrid effect. Of course, any PhD thesis doesn't come, well, most of the PhD theses don't close themselves, so there's still some work to be done. For example, the finite element model that I showed you here to predict the stress concentrations near the lamination is not really perfect. There are some things that need to be worked out to be able to make it work all the time. Also, capturing dynamic effects and local stress concentration is really important to be able to capture to predict the strength of our composites, as I showed you before. And also, I think our model can be extended to this interply dispersion. And using these 3 goals of future work, I think this can work together to predict the strength of any kind of fiber hybrid. Okay, so finally, Some of the work presented here is also published in these publications over here, and some of them are actually in the FiberMod website, these two, so please go have a look if you want. Thank you for your attention.
Thank you very much, Francisco, for this very clear presentation.
Thanks.
And then there is time for discussion. I would first introduce the members of the jury, for those who are watching us on video, also in the sequence that they will ask questions. So we have Dr. Jeroen Zoete from the Department of Materials Engineering of this university, and also Secretary of this jury. Then we have Professor Yannis Pontikes, Department of Materials Engineering as well. Professor David Sevino, Department of Materials Engineering, is online as far as I understand. Hello, David.
I'm online, yes.
Then we have three promoters. Dr. Lennis Gorbatic, there. Department of Materials Engineering, Jentel Swolfs, Department of Materials Engineering, and finally as promoter, Stepan Lomov, Department of Materials Engineering as well. Professor Soraya Pimenta of Imperial College of London, United Kingdom, is excused for today, but has given written advice. And I myself am Max Seefeld from the Department of Materials Engineering, and I've been asked this morning by the faculty to replace Professor van der Biest as chairman, being the oldest of the left jury members who are no problem. Right, so we can start with our questioning, and maybe you can start.
Francisco, I want to first of all congratulate you again on the amount of work that you did in relatively short time. Also for the presentation, I think you bring a relatively difficult and complex subject in a clear way for the wide audience.
Yeah, hopefully some online.
Indeed. I think you made a very important contribution to the hybrid composite world by constructing a model that allows people to predict the behavior of these UD hybrid composites, which will be for sure very important. So congratulations on that. As you already mentioned, more work could be needed. For example, implementing the dynamic stress concentration with one of the things that might be one of the next steps to go through. And then, of course, also other hybrid composites. Not only the interply hybrids, as anti-yarn and so on. You mentioned that you work on interply hybrid composites because they're quite easy to manufacture. Does it mean that the others are commercially less viable, or?
Well, there is interply, so bundle by bundle dispersions. They exist commercially. There is a company at least that we know that manufactures them. The intra-yarn, those, well, at least very successfully with fibers very well mixed with each other. I don't know anyone who has been able to do it.
Okay. You already answered most of my questions during the preliminary event, so today I have more of an important question, I would say. You know that I'm a fan of X-ray computed tomography, so my question would be, if you move towards other tests such as compression or bending, for example, then if you want to, for example, validate delamination instead of only fiber weights, what kind of improvements would you need to synchrotron CT or lab CT for that matter in order to make that possible, or to have a CT as a validation method for those things?
So you mean improvements in the method of
Yes.
the tomography itself?
In your experience, what would be the biggest improvement that is needed to achieve?
Well, for sure, for example, the lamination, what I'm thinking right now, is that the lamination propagates in a quite fast manner. So in order to be able to get several data points of the propagation of the lamination, then we need to get these scans quite fast. And by fast, we did here in our thesis, in my thesis, of 9 seconds, but I think we would need to do it even under 1 second. There's also perhaps something that we can do if, for example, if we want to look at the compression. One of the most important things that determines the compressive failures, fiber misalignment or imperfections. And for example, carbon fibers, epoxy, their attenuation is not that different, so it's not that easy to see them. And the interface, so where the fiber ends and where the matrix starts. So improving a bit the resolution would also be necessary. Depending on the fiber type, yes, I'm thinking carbon fiber because they are the most difficult ones to see, or one of the most difficult ones to see.
And then maybe from my side, the last question based on the presentation. In one of the first slides, you showed that there's a pattern in hybrids and carbon fiber composites, based on which you can predict that there's something happening.
Yes.
But this is something that is happening on a very small scale. It's not something that you can, or you can correct me if I'm wrong, that you can use it in real-life applications.
Well, if we use this composite, so what you see there is actually the carbon plies are breaking. That's why you get this pattern. So if we have an application even larger scale with the same stacking sequence and with the same loading condition of tension, that's the part that I would say it's more rare that we have only pure tension in the composite. I would not see any reason why this would not happen even in a larger structure.
Would you have a way to monitor it? I mean, is it really a warning system?
Yes, I think so. If we have some way of getting an image every minute, seconds, and I think with a nice algorithm you can actually detect the pattern, then I think, yeah, there can be a warning sign to whoever is in charge of it to go and say, this needs to be replaced.
Thank you very much, and congratulations.
Thanks.
Thank you, Leuven. Yes.
He said it already, it's a nice board. I mean, we said it before, but also presentation. I've been asking myself if I understood more this time than the previous time. But I think that's a good sign that both the presentation, perhaps my evolution of the topic has been positive. So no more congratulations. Let me ask a few questions. Being an outsider sometimes is difficult because I think this kind of more existential questions, and also I think the time can justify that. So I will be teaching about composites also. I have this construction of the Aula course. So what is going to be a composite material? What should I say to my students that composite is?
That's a good question. So composite, in my view, it's a material that is heterogeneous. So it has two or more materials combined, and each of them should make the other one better. So the combination of the two should turn out to be a better material than any of them separately.
Right. I wrote myself about definitely two different materials.
Yeah.
And also you put an extra element, the synergy. Okay. I have another PhD in you got me a bit hooked on your slide with the wind blades.
Yeah.
The PhD is about recyclability. So on one hand, yes, the metals might not be as good as composite, or some composites at least.
Mm-hmm.
The metals might be perhaps more nice to the environment because you can put them back in the furnace. What am I going to do with the blade that is composite material? How can I recycle that?
Well,
Do something about it.
yeah. Well, it's not my expertise recycling of composites, but I have some knowledge myself. So most of the recycled composites that I know of, they are not continuous fibers like I showed here. I actually could have added that as well. They actually have short fibers randomly oriented. So what you can actually do is try to chop the parts of the blade, try to remove the matrix via pyrolysis or chemical dissolving it, and then put back the fibers to make a new composite. Maybe. From my knowledge, I think this is what the approach is. What are the techniques exactly?
Okay. So you defend, I think that the interply, you said the hybrid. So
Yeah.
I asked the time, but I didn't know the answer. Is that really happening? Because again, you saw the chassis of the BMW thing.
Mm-hmm.
I was asking myself, what is this made of? Maybe hybrid is so good, it's really happening.
Yes, now I remember we did discuss that before, and I did not turn out so well before, but I think now I have a better answer to that.
Sure.
So indeed, those wind turbine blades, first of all, they are being made now also on hybrid composites, because classically they are made of glass fiber composites, but if you want to make them longer and more efficient, then you need to add some carbon. Now going just with carbon, maybe that's not so economically viable, but you have a mixture of both, that is. Also the airplane, I forget the name, that's the I mentioned it last time, I think it's the Dreamliner that has hybrid composite in his wings and other applications. So they are being used.
This happened, nice. But here's another thing. On your composite, on your hybrid, you're saying I want a ductile fiber.
Yeah.
And you're saying glass is ductile. Is that the case?
It's more ductile than carbon.
More ductile.
So
now again I'm like stuck. Why are we not using metals, metallic fibers? We can still have micrometer thick fibers.
Yeah.
If I remember what they are.
Yeah, they are.
So
I think the issue there and why we are not using them, but maybe other options, is weight. So steel fibers are still heavy fibers, because they are still 7.8 or 7.9 grams per cubic centimeter. So even if you make it half-half with plastic, it's still going to be about 4 grams per cubic centimeter, which is higher than glass or carbon fiber composite.
Lightweight, light metals.
Yeah.
Okay.
Yeah. So.
All right. Two more and we're done. In your schematics, you have these figures, right? And I see fibers, different orientations, but to me it looks like fibers in a vacuum. If you would tell me, I think that's the way you analyze the whole system. It's like I don't see much of discussion on the thing next to the fiber. In that case, your polymer.
Yeah.
Right. So if I take your model and I say no, there is a polymer in between, or it's actually nothing in between, vacuum, would there be any difference in the output?
Yes. Yes. For sure. So actually, I think it was Fabio that asked me that question at home the other day. What's the difference? Why do you have a matrix after all? So I think that there are different things. So if you don't have the matrix, one fiber will break, and all the other fibers will share the load equally. So there will not be these stress concentrations locally. But that's not all. Fibers work very well in tension, but imagine putting compression only on the fibers. That will not work. And maybe not compression purely, but think of bending. If you try to bend fibers, that holds no resistance whatsoever. So you need the composite.
But in your analytical work, does that somehow be taken into account? Like if I tell you modify now your resin from resin A to resin B, will your model somehow react differently?
Yes, yes. So speak a bit more technically here. So if the matrix is stiffer, basically the recovery length when you have a broken fiber will decrease. And on the other hand, if the matrix is more ductile, more plastic, then this ineffective length will increase. And the way this typically works is that if you have a higher ineffective length, so less, more compliant matrix, it generally gives you a lower strength of the composite.
Okay, so the model, there are some parameters in your modeling that would
be affected by the matrix and so on. So yeah, indirectly they will influence the strength of the composite.
Okay, and to honor the room that we are, thermodynamics, it's an easy one.
So that's the entropy equation.
No,
Strictly speaking, not correct.
but you did have, I think it was slide 36, it's all about the energy. Okay, so a classical metallurgy, we think of ceramic or granite, whatever. We think of kinetics. For you, kinetic is not.
So kinetics were not taken into account here, but they would play a big role not only on this, but actually on the dynamic stress concentrations. That's where kinetics actually do play a big role. Here, on the wave of the delamination propagating and how this affects, in our model we do things in a static way, different delamination lengths, but still static. So for sure there are effects there, but I think that's the next step. Here we already, I think, our model for the lamination was already quite heavy and difficult to run, so adding dynamics on top of that in the next few years, hopefully.
I was lying last time, I swear.
Okay.
Fiber, for me, fiber is kind of standard. If you do ceramics, you do concrete.
Yeah.
People get away with composites to do viable distributions.
Mm-hmm.
Isn't that standard? Maybe composite, something like that? Or you
I
present
don't understand.
like a standard way of measuring,
Yeah.
and nothing extraordinary, like trivial.
Mm-hmm.
Is it extraordinary in composites to do viable distributions? I mean, for me, it's like the thing you read in the book.
Yeah.
You should be doing viable distributions.
You're asking if we should be doing other kinds of distributions if they are
No. I'm
altered.
saying if there's any novelty in doing viable distributions, it's part of your thesis. It
Mhm.
implied to me that that's something new.
Mm-hmm.
But I thought that this was taken for granted that you should be doing viable distributions.
So the fact that we use Bible, that I don't think it's new. I think the novelty here, or what we are aiming to do here, different from other people, is that we are testing larger data sets. Because people tend to use sometimes only 20 fibers or 50 fibers, and we saw how much scatter that gives.
Ceramics is 12. Get away. Yeah.
It depends on the modulus.
Thank you very much, Mr. Chairman.
Thank you.
Thank you, Yanis. David?
Yes, can you hear me?
Yes, very well.
Okay, great. First, thank you, Francesco, for this nice presentation. As it was pointed out, it's not an easy task when it's about modeling. Present modeling things to an audience, but you did it very well. I have only a few questions, basically 3 questions. And the first one is about the scales you have investigated. So basically, you look at the fiber scale, so the micro scale, and then let's say the ply scale. So I think we can associate this ply scale to the macro scale. And this is quite okay when you have UD, but as you have one slide illustrating that we have also a woven textile or braided textile, and then there is an extra scale coming in between the micro scale and the macro scale, which is the meso scale, so the tall scale or the yard scale. So how far are you to, let's say, add this mesoscale into your models? Is it something that is of interest? Is it something that would be compatible with the already established modeling framework? Or do you need to start from scratch again to include the micro, meso, or micro scale?
So can you hear me well?
Yeah.
Okay. So if I may ask again, your question is about adding a macro scale on top of the meso scale that we already have here.
Yeah.
Okay. So can you please mute your microphone for a second? I'm hearing myself. Thank you. Okay. So the way I think this would work is that we are predicting now the strength of a meso level bundle, indeed. But I think once we know the strength and the variability of strength and other parameters, other like stiffness, like failure strain, other things, of our mesoscale level, I think we can input this in a finite element model, which is a macro scale, and adding some of this into such model, I think that would bring us to the next scale. Now I'm done with my answer.
Okay, so there is no, let's say, extreme difficulties in adding a mesoscale into this framework.
I don't see that from my point of view. So we are working, just to clarify, we are working here on the micro, so fiber level, and on the stacking sequences level on the meso scale, in my view. So what we would be adding is a macro scale. Does that make sense?
Yeah, okay. Well, it's about definitions of what is
of
micro, meso, scale. Okay, but we still need the scale, I think, anyway.
Yeah.
My second question is, yeah, I mean, you have evidence that the carbon fibers, they tend to stiffen when they are stretched.
Yes.
So you have a positive, let's say, slope for carbon fibers and a negative slope for glass fibers.
Yes.
Yes, okay. Is it something that is considered in your model, or do you use some fixed values?
Yeah, indeed, I didn't consider the stiffening or decrease in stiffness of the fibers in the model. Because, well, as you may imagine, the PhD thesis doesn't occur linearly with the chapters, but we got this data analyzed finally, yeah, more or less at the same time in parallel with the model development. So, in order to maintain the modeling work consistent from the beginning, I didn't add this halfway. I kept it constant, always. So the stiffness is a fixed value, and that doesn't depend on the applied strain. But our model is prepared for that. I just didn't turn on that option.
And do you think you would have a huge impact on the final results? Would you change not the full picture, but at least would you end up with different, I don't know, damage mechanisms, different types of failure mechanisms?
So the way I think about that is that if we would add this stiffening effect to the carbon fibers, we're basically increasing the stress faster as we apply the strain. And since our Weibull distributions are stress-based, basically we are breaking fibers at the earlier failure strain. So indeed we could anticipate slightly the failure strain, and then if you look for the glass fibers, if the opposite happens, we can actually separate a bit more the failure strain of carbon and glass. So that can have some influence, but yeah, I cannot say exactly how much.
Okay, thank you. I have a last question about the Weibull distribution. So you make it clear that we need a large set of data to come up with reliable Weibull parameters. And basically you investigated two techniques. First, I mean, having a tensile machine with that diastrom machine, or and then using a synchrotron and do all the things you have done, very difficult things. So it seems that, yeah, getting a large set of data is quite difficult, because either you need this very specific machine from diastrom or Thermotechnical, I think they are quite expensive, and you need how to use them, or you need to go to synchrotron, which is maybe even more difficult time-wise. I mean, you need to prepare all your samples, you need to write a proposal, and so on, so it takes time. But eventually, I mean, what would you prefer to go for the sort of diastrom machine, or would you prefer to go to Grenoble and test again your samples on the synchrotron?
That's a good question. So if so, I think in terms of time consumption, yeah, there are competing factors there, because for the single fiber tests we need to mount each fiber and yeah, test them and wait for the test to be done. But then from that on, well, it's quite straightforward to process the data. Even MATLAB has a function to just get all the strengths. Getting all the strengths, it gets you immediately the Weibull parameters. On the other hand, if we want to go to the synchrotron, well, first we have to go there. Second, we have to test the sample and get a successful test. But the most key difficulty there is to analyze the images, because that's, I think, the bottleneck right now. Luckily, I think in our group, and hopefully this will be working very well soon, Christian is developing an automatic detector, automatic data analysis of this data. So skipping that step, getting that step automatically, then I think the second option of going to the synchrotron would be a better option. Of course, we need to plan things correctly to go if we want to go there often or not, and when we go there, which data sets do we need? Well, if we have a diastron machine, then we can, in our lab, then we will be able to do it every day if we wanted to.
And I think one additional key difference is that when you test fibers on diastron machines, you are testing individual fibers, whereas in the synchrotron you are using fibers which are bundled together or grouped together with the matrix. So maybe a synchrotron is from that perspective a little bit more realistic or closer to what is the real composites than individual fibers. I don't know if you would agree with me on that.
Yeah, I would agree completely on that. So if you want to, because indeed, when fibers are embedded in a matrix, their properties may change a little bit because the surface defects may be affected. While if you test an individual fiber, that is not the case. So I completely agree with you.
Okay, thank you, Francisco. I have no more questions.
Thank you very much, Malik. And then we come to the promoters. Alissa.
Thank you for your presentation. Very clear today. I have a few questions. Going back to the major challenge, looking at hybridization as a strategy to design and produce materials with properties that we cannot achieve otherwise. Right?
Yeah.
So I think that's the goal of hybrid materials. And a unique combination of properties. Right? So if we think about carbon fiber composites, and let's say we would like to make a new material that has a high yield stress and high deformation, what would be the ideal fiber, other fiber type, or other fiber types to be combined with fiber to produce such
So by yield stress, do you mean that we would have sort of a pseudo-ductile, or can we allow a low drop?
Well, if we look at your carbon glass,
Yes.
right, so you would have some kind of plateau there.
Mhm.
Let's say we would like to stick to this type.
Yeah, yeah. Well, if that's the criteria, then what we were talking about metal fibers, I think that could be a way to go, because they are still very stiff as carbon fibers, but they have a much higher ductility, much higher failure strain. Because when we go to, if we think about very ductile fibers, I would think of polymer fibers. But then I think, the moment that the carbon plies would fail, we will get this load drop, like in June's work or Marina's work before. And then we still can get the ductility, but to get this plateau, then I think that's something, if you want something very ductile, then I think, for example, metal fibers could be a way to go. Or another kind of very stiff fiber, but also very ductile. S-glass, PBO, we talked about that recently. So.
But is there a kind of constraint or limitation or opportunities
Mhm.
on the other side in terms of stiffness? Because you are showing in your previous works this banana curve, right?
Mhm.
The properties of the fibers. So you do have some limitations in choosing properties from the traditional fibers. So how would you pick the properties? Because now you speak in general terms. Let's take tactile fibers. You know, if we take polymer fibers and have significant growth stroke,
Yeah.
these fibers are not stiff enough. So
Yes.
what is the optimal, let's say,
Yeah.
that we need to take, not to have a lot of
Yeah, in that case, indeed, we need to have something that is still stiff, not probably would not need something that is as stiff as carbon, because those fibers would be also very brittle, but something that maybe slightly less stiff than carbon, but also ductile. In that case, as I was saying before, if we take the classical glass fibers as I've used here, we still get this curve. So I we want perhaps something with the same stiffness as glass, or a bit higher, and more ductile, right? Now, I was thinking, indeed, S-glass, for example, meets this criteria, but it's still a glass fiber. But if we take another kind of polymer fiber, I was thinking indeed of PBO, it's still very stiff, but more ductile. So this could be an alternative, but then it's more expensive. So those are other constraints. Yeah.
Okay, then you've raised my question. So how do you see advantage of choosing multiple fiber types? Because in your work it's only two fiber types.
Mm-hmm.
You mentioned today
Yeah.
working with multiple. Is there advantage to it or not?
Yeah. Yeah. So using that to our advantage, then we can probably have something even more gradual than the plateau we have. So maybe we extend the plateau if we have multiple fiber types, because if we have, let's say, more fiber types, and let's say 3. Let's not complicate too much. And let's say that the first plateau is happening because the carbon plies are fracturing. Then if we get a second type of fiber that will fracture afterwards, then we can extend the plateau and then continue with the more ductile fiber types. So that could be a way. And if we have more fiber types and more fiber types, then maybe we can extend even more this plateau.
So what are the other strategies besides hybridization that could be used to achieve similar goals? Do you think there are other strategies?
I'm not sure actually if I mean, from my point of view, to get the best out of the two fiber types and add some safety, get some warnings, which other strategies because in multidirectional composites, for example, which is kind of the other option, okay, we have some warnings, we have some matrix cracks, we have some delamination that can serve as a warning, but still the failure will be at the first.
Well, architecture plays a significant role.
Yeah.
So if you work on fibers, there are
Mhm.
possibilities to design
Yeah.
similar elements
Mhm.
to architecture too. So the fiber types of architecture.
Yes. Yeah, probably looking into the bio-inspired approaches. That may be a way to add some ductility to brittle fibers, make them fail gradually as we choose and not as they fail naturally. So yeah, indeed, discontinuous fibers, but controlled discontinuity is not random.
Maybe last question. Not a technical question, but what would have you done differently? Now looking back at all the work that you have produced and all the paths that you have taken,
Mm-hmm.
would you do something different?
You can say no, everything was perfect.
But for sure, the stress concentrations work differently if you have this kind of morphology in the fracture surface. So that's something that we would need to adapt over there. Also, the way the fibers are non-linear in their behavior, something must be adapted to that as well. So,
what do you think would change in the cluster formation, for example?
Good question. So, if the fibers stress concentration change, how would they change? So probably they would extend a bit the region where the stress concentrations are applied, because as we've seen with the matrix, if we have more plasticity, then this region of stress concentration increases. So probably these clusters would perhaps be a bit more dispersed versus the coplanar, if you agree with that.
Yeah, I think so too, and that could potentially be interesting, because the coplanar ones that are critical are the most critical. So nobody really knows, I think, but I think it's conceptually quite interesting to try it with that as well.
Yeah.
And the second question, and my last question, is related to the synchrotron. Now you have done think we also realized that there are certain things we wanted to achieve and they didn't really quite get there. So if you have one single experiment you could do in sync.com for hybrid composites, what would you do differently and what type of test would you be doing? Just one test.
One test, it can be any test. Tensile?
Yeah.
I'll stick with the tensile still.
Yeah, I would.
But, but I have an answer for that. And it's related, well, if I can find that. Yeah, it's actually, I went straight to the slide. It's related to this hybrid composite here. So when we created it, we thought, okay, we're going to make a glass fiber layers here to stop the interaction between the carbon fiber layers. And we didn't really achieve that. Actually, they failed. The 3 carbon layers actually failed simultaneously. So what I would have changed, that if I could go again, I would add more glass fibers and see each ply fracturing individually and what would trigger it. So that's what I would.
Okay, thank you very much.
Right, I will also ask a question. I will start with a small story. I was once present at some gatherings, technical gathering of aeronautics people. And there was discussion about admissible stress which they can put in designing a plane. And it all came to Leuven monomers. Because in norms for calculation of design strain, it was written M equal 4T. And somebody in the audience, he maintained position that M should be 60. And this gave enormous increase of design stress, and then of course enormous economy of just everything, including cost. And then the words the people used one or another, they are not pronounceable in normal audience, so I wouldn't repeat that. So this was very heated discussion. I was very much surprised to hear that. And this was a question about 14 against 60.
Yeah.
Now, my question to you is, why carbon companies do not argue like this? Why array isn't shouting on Excel, our carbon fibers has M modulus of 22, and Excel said, yes, but why this doesn't happen? Why M is not, or why both characteristics are not measured and presented as standard reference values in characteristics of fibers, carbon fibers included. If they are so important, if you have one dissertation about it, another dissertation, a third dissertation,
Yeah.
why?
My best guess, and this is not a good reason, I think that, well, these tests are time consuming, and I hope that's not the reason why they are not doing it, but I think they just find a better way that they get a bundle, they do the tension test on it, and they get the strength, and are able to back calculate the strength, average strength of the fibers. This is much easier than doing single fiber tests.
But this means that nobody really needs a sculptor.
Well, if we want
Like
to model...
Like these aeronautic guys, they needed it because this affected their decisions and finally money and safety of passengers.
But this, but wait, this modulus that you were arguing was of the composite strength or the fiber strength?
No, composites, of course. So
of composites. Yes. So, I mean, there, the importance is, okay, how reliable is this average strength value that we are using here?
Exactly.
Is it 16 worth of reliable, or is it 14, only 14? And there I think it's about safety, but in composites, the fact that the fiber has a different modulus, well, actually I cannot recall now, but one of them will yield a higher strength or a different strength, but still a gradual process. So fibers will still break gradually, accumulate. If you have a lower modulus, they will accumulate from an earlier stage and compared to higher modulus. So I think the views are a bit different in composite Weibull modulus or fiber Weibull modulus. Because one influences the strength of the composite, the other one is already the scatter of the composite.
Okay.
May I ask also, by the way, when was this discussion?
things. I was wondering this.
This discussion was yeah, like a year and a half ago.
Okay, recently. Okay, thanks.
Thank you, Stepan. I was wondering whether I was supposed to ask a question in this new role, but
If you want.
Stepan suggested yes, so I have one. Would you expect, if it comes to the prediction of the local stress concentration,
Yeah.
expect an improvement of your results if you would embed details of the internal structure of the fibers and all of your interfaces into your modeling approach, so the nanoscale, if you wish?
I think so, yes. So just by adding local stress concentrations, we've discussed that before. So now, I think for about a year now, or maybe even just a few months, someone actually was able to measure the intrinsic strength of these carbon fibers. So just by using this value and the local stress concentrations, we can already say, okay, if this fiber just in this small region exceeds this value, it will break regardless of having a defect or not. So if we still add the defects on top of it and these local stress concentrations, we get the best of both. Now the problem there is computational time, of course. But if there is a way to combine the two things, another layer of a scale, then yeah, that would be optimal.
Concerning the interface?
Concerning the interface, you mean surface flaws or the interface as in debonding from the anything?
Surface structure, roughness to start with, maybe.
Yeah. So for the local stress concentrations, that could I don't know exactly how that would play a role, but indeed the surface of the fiber could play a role in debonding. When the fiber breaks, it will debond from the rest of the matrix. Transfer the stress concentration not to the fracture surface plane, but in another region, and break fibers that are weaker but not exactly there. So yeah, again, that would. I think the more detail we add to these things, the better we will get in general.
Yeah, of course, it's always a trade-off with the computation.
Exactly, exactly.
Okay. Any questions from the audience?
I have a curiosity. I saw when you characterize your fibers that some carbon fibers are different diameters.
Yeah.
Did you take that into account in the model? I mean, does that play a role if you use?
So the
if the fibers are smaller.
So you mean the scatter
the
of
diameter of the fiber yeah.
So you mean that this fiber type HS40 was 5 micrometers versus the T700? I didn't really look too much into that, but I can predict more or less what would happen. Is that so? If the fiber is bigger, these local stress concentrations play a big role compared to the average stress, because if you average the stress over a bigger fiber, then the average stress concentration will be lower. So you would be under predicting the failure of them. So as close as if you go to infinitesimally small fibers, I think these stress concentrations will be a bit more accurate. That's my view. Questions from YouTube? No?